Yeah, so I'll start the tutorial. Is my screen visible? Mm.
Yes,
Yes.
sir. It's
Yeah.
visible.
Yeah. So, have everyone seen the tutorial once? Right? Like, have you downloaded it from the Moodle?
Yes,
Yes,
sir.
sir.
Okay. So these sessions are not so formal. So if you want to stop me in the middle and ask something, you're free to ask. And we'll start with the first question. So if someone hasn't read it, so you can read it once, then you can start. So basically, in this question, we have to calculate the losses, and we are given the resistivity, and we are given the current carrying density of the conductor. So basically, the formula for loss is I square R, and as we are not given the resistance directly, we'll have to calculate it from the resistivity. So the formula for resistance is rho L by A, and so you can basically uh, put the value of R in here, and then instead of current, we'll have to use the carrying density, which is rho, and the area of the conductor. We'll assume the area of the conductor as A, and uh, write I as sigma into A. So then you can just plug in the values that are given, and for calculating loss per kg, we'll have to use the specific gravity of the conductor, and then we can so we can calculate the final answer. I guess this is a simple question, and the main, like, there's one thing that you have to keep in mind in this question, that the resistivity is not given in the SI unit. It's given in micro ohm per centimeter, a micro ohm centimeter. So you'll have to convert it in ohm meter first to get the right answer. So does anyone have a doubt in this?
Sir, one thing, so here if we like convert rho first to rho into 10 to the power of minus 6 ohm centimeter, so 10 to the power minus 8 ohm meter,
Right.
and then we multiply with sigma, then with sigma we convert like 10 to the power of minus 6. So that way also we can do, right? That also is
Yes,
fine.
yes, yes. This solution is like a bit confusing. You can see this one, like, yeah.
Okay, sir.
You're saying it like this, right? So next we move on to the next question. In this, we are given an battery of E volts, and it has an internal resistance R. So we, we have to connect an external resistance capital R, so that the heating takes place at its maximum capacity. So first we'll have to like the internal resistance is connected in series with the external resistance, so we can calculate the current, and it is given as E divided by capital R plus R. So we can use the formula I square R, and then we can differentiate it with respect to capital R and find the value of external resistance at which we will get the maximum heat. So we get this answer, R equals to small r. In the next part, we are given that three-fourths of the total energy developed by the generator is absorbed by water. So in this case, the total energy developed, which is E square divided by R plus R. Uh, so we'll multiply this by 3 by 4 and equate it to the heat supplied. and we'll get the value of capital R in that case. So is this clear?
Yes, sir.
Yeah. So yeah, you in the next question we have an inductance of. So yes, we are given an inductance of 0.25 Henry, and the voltage is given as a function of time 4t. So the voltage applied uh, in case of an inductance, the voltage across the inductor is L di by dt. So we'll just equate it to the voltage that we have given and calculate the function of I with respect to t, which will come out as 8t square. So as it is an monotonically increasing function, the maximum value will be at t equals to 5, which will be equal to 8 into 5 square, 200 ampere. In the next part, we have to calculate the RMS value of current. So we'll use the simple formula for RMS, like we'll first integrate it from 0 to 5. I square will integrate and then divided by total time to calculate the mean, and finally we'll take the root. So we get this answer. So in the last part, we have to calculate the energy stored by the inductor, total energy stored. So you might have done this in during your JE. It's a simple formula, half Li square, and it's easy to derive. Like you can use it. Like the voltage across the inductor is L di by dt, and the current is I. So the power developed in at a particular instant is Vi L di by dt into I, and you can integrate it from 0 to I, and you will get this uh, half Li square as the expression for total energy stored. Okay, so now we move on to the next question. Yeah, so in this question, we have two resistors connected in parallel, and we are given the total current, I guess. Right, we are given the total current that is flowing through the circuit and the power dissipated through one of the resistance. So I don't think I do. I need to explain this question. So this is fairly simple. If you have doubt, you can ask. You can stop me in the middle of at any time if you have any doubt. So in the next question, we have two resistors connected in parallel, 8 and 12 ohm, and one series. And we are given the total power dissipated. So basically, first we'll calculate R effective. Like the if we are given the total power dissipated and the voltage, we can easily calculate the R effective of the circuit by using V square by R equals to the power dissipated. So we can calculate R effective as 5.714, and then using like when the using the parallel combination, we can calculate the R effective of the this uh, parallel circuit, and then add the series resistance to it, then and calculate the series resistance by equating it to the R effective that we have already calculated. Uh, so yeah, in the next question, we have to calculate the magnetic flux density at the center of a square in which current is flowing. So I don't think this is important. This is an important question if we consider the course, but this was just given to brush up your JE skills, so you can try it on your own. You might have learned this formula in your, and you can just put in the values and get the final answer. So yes. So till now, does anyone has a doubt?
No, sir.
Okay. So yes, in the next question, there are two voltmeters connected in series with a battery. The battery is providing 240 volts. So basically, in this we have to just use a simple concept that the voltmeter reads the reading uh, of the voltage that is developed across itself. So we'll first divide the total voltage in between the resistance, so that will be divided in the ratio of those resistance, and then we can like, yeah, so then we can divide the voltage across them using this formula. uh, Okay, so in the eighth question, there's a capacitor that is first charged using a voltage supply. So initially, a voltage of 250 volt is applied, and we are given the distance between the plates. So we can calculate the capacitance, and using Q is equals to CV, we can calculate the charge on the capacitor. Then the distance between the capacitor is increased. So if we increase the distance, then the capacitance of the capacitor will change, but the charge that is on the capacitor will remain the same. So we are assuming that we have removed the power supply, the voltage supply, and so the charge on the capacitor will remain the same. So now we have to calculate the change in energy. So the energy stored in a capacitor is half Q square C divided by C. So as the charge is constant, we can easily calculate the energy by using the difference in the distances from initial distance and the final distance. And so that comes out to be as 138.34 microjoule, which can be converted into ergs. So the ninth question is also fairly simple question. So you can try it on your own. And if you have any doubt, you can ask me after the class, or it's a simple question. So I don't think I need to discuss it. Uh, yeah. So in the 10th question, we are given like there are n groups of series, each having m parallelly connected resistances. So we will consider so the basically one of the resistances is removed from the circuit, and uh, we are asked to calculate the current change in the resistances. So basically, initially the voltage across each group is E by N, because there are n uh, n equal resistances connected, n groups of equal resistances connected. Then we can calculate the current in each of the rheostat, as this as the total current is E by NR. So this will be the current across each current flowing across each rheostat. When one of this rheostat is burnt out, then we can the total resistance changes, because so basically in the group where there are only m minus one rheostat left, so the resistance of that group will be R divided by m minus one, and for other groups it will be R divided by m. So you can calculate the total resistance. From that you can calculate the total current, and then you'll have to calculate the current in each rheostat for the faulty group. So that will change because now there are only M minus 1 resistances in that group. So, and then you can calculate the percentage increase finally. So the current will increase slightly in that group. So moving on to the next question. So yes, in this question, you are given two cells which have an internal resistance and okay, they are the same cell. Just a second. Oh, you are given a single cell which has an internal resistance and you have to calculate it. And so I think it's a simple question. Like you have two variables: the voltage supplied by the EMF across the cell and the internal resistance. So the main thing to note in this question is that the terminal voltage, when we have to calculate the terminal voltage, we will include the voltage drop across the internal resistance. So that's the main motive of this question. Otherwise, this question is simple. Then okay, so in this question, an external there's a cell which has an internal resistance of 5 ohm, which is connected to a resistance of X ohms. Now we have put in another resistance of 6 ohm, additional resistance of 6 ohm across the battery. So we have to find the value of X so that the power generated is still the same. So you can just calculate the power for each of the cell and equate it. So the thing is to notice that the power that is calculated, it's only calculated across the external resistances. Like we do not include the power dissipated across the 5 ohm internal resistance. So you can just equate it and calculate the value of X. Yeah, so in question number 13, there are two cells that are given with each having some internal resistance and that are connected to an external resistance. So you have to simply apply KVL and KCL and solve this question. So I don't think I don't need to explain this. You can try it on your own. So does anyone has any problem, like any doubt or something till now?
No, sir.
Okay. Uh, so I guess instead of explaining, just read the next three question, and if anyone has some doubt, you can ask me. Like they're fairly simple questions. So so this tute was just an introductory tute. So I don't think there's any difficult question that you and you will not be able to solve. So just have a look, and if you have any doubt, you can ask. If you have any doubt from the lecture, you can also ask here. That's fine. So if no one has any doubts, we can end the session. You can ask me on Teams if you have any afterwards. Okay.
Sir,
Yeah, yeah.
excuse me. So
Yes,
what
yes,
is
yes.
the meaning of what is the meaning of condenser voltage?
So condenser is basically the capacitor. So it is the voltage applied across the capacitor. Condenser voltage, or the voltage across the capacitor is the condenser voltage. Something.
So in number 15, then we have uh, this are differing voltage that is dependent on time. So which one will be called the condenser voltage?
Let's find it. In question number 15. uh, So the condenser voltage will be like, it will be varying with time. You can calculate the either you can calculate the steady state voltage at the end, like at the end of 10 seconds, by simply putting the value of 10 in the, like you'll get a voltage of 2000 at the end of 10 seconds, I guess. So that can be called as condensed voltage.
Like, because after that it becomes steady. That's why.
Yeah, that's
Okay, okay.
any other doubt? Okay, so we can end the session.